Now, in the last chapter, we talked about the effects of magnetic fields on magnets and on moving charges. We learned that a magnetic field would exert a force on a moving charge, but we know from Newton's third law that there will be an equal and opposite force from the moving charge on the magnet, and that force must be magnetic in nature. What this suggests is that this moving charge not only responds to a magnetic field, but that it will create a magnetic field of its own. And so that's what we want to study about today, is how a moving charge creates a magnetic field. Well, the most natural place to find moving charges, and a significant number of them, is in a current. And Oersted found that if he took a piece of wire and placed it so that it ran along the line of a compass. So the compass is pointing north, lined up with the magnetic field of the Earth, and he places the wire along that same line. Then when he connected the wire, the magnetic dipole, the north pole of the compass, deflected away from the line it was on before, suggesting that a new magnetic field was added. Now you can do this yourself with a compass and a piece of wire. We'll do some of these tests in class. So if we take a piece of wire, pass a very strong current through it, and look at iron shavings, which tend to line up with the magnetic field just like a compass would, then we see that the magnetic field around the wire runs in circles, concentric circles with the wire at the center. We can get the direction of the magnetic field through a rule that Oersted came up with. That's another version of the right-hand rule. The basic idea is that you want to take your fingers and you want to place your thumb lined up with the current. So if the current is going up, you place your thumb up. If the current is going down, you point your thumb down. And then your fingers, in their natural curl, will point the direction of the magnetic field, the direction that the north pole of your compass will be deflected. So if we go back here, if the current were coming out of the page, then if you put your thumb along this wire, you'll find that your fingers curl counterclockwise, suggesting that this magnetic field goes counterclockwise. If the current were running into the page, you would find that the magnetic field was clockwise. Oops. Now, a couple of things we find experimentally. The closer you are to the wire, the more strongly the compass needle gets deflected. So that suggests that the magnetic field is stronger in closer. For a given current, the amount of needle deflection depends only on the radial distance from the wire. So there's nothing else that matters. It doesn't matter which direction you're in. It doesn't matter anything other than how far away from the wire you are. At a given radial distance, increasing the current increases the needle deflection. In other words, the magnetic field is going to depend on the strength of the current. If we flip the direction of the current, the needle will also flip its direction of deflection. So if we draw directions of needle orientations at many different points all around this, we get concentric circles with the field being stronger in the center. That's why the lines are drawn closer together, and weaker on the edge. Putting this together, essentially what we find is that the magnetic field, its direction we found before, but it's got to be proportional to the current and inversely proportional to the distance away from the wire. That we can discover experimentally just from this information here.